and go back to our Proxmox shell. But this time we exited out of our Ubuntu Prox user. And if I was to hit up arrow again, that's going to run the script to generate our new user. That won't work. So what we need to do is type in su space a dash and Ubuntu Prox. That way we switched back to our Ubuntu Prox user. Then I can type in ls and pick up where we left off. Another thing to note is if I click Data Center and then I click Users, the only user we see here is root. The reason for that is the user we created is specific to the OS that runs Proxmox, not the Proxmox UI itself. But that's okay in this case. We just want to have a separate user so our root user is clean. Now we're back as Ubuntu Prox and I can edit script 2b. Now script 2b is a pretty large one, so it might actually make sense to review this in our GitHub. If I scroll all the way up and then pick the 2 folder and then pick 2b, this one might be a little bit easier to read here. We only have to edit lines 34 through 60. This commented section here explains a little bit more what will be built. We'll have 9 VMs in total. The first VM will be our admin VM, and this will be VM ID 200. Then we'll have 3 VMs, which will be K3s, 01, 02, and 03. All 3 of these VMs will be met for the Kubernetes control plane, and these will have VM IDs 201, 202, and 203. Then we'll have 2 VMs that will be our Worker VMs. They could be thick provisioned if we had a thick LVM from step 0, but in this demo we don't, so they'll be thin provisioned. These will be VM IDs 204 and 205. And then finally, we'll have 3 VMs that will be our persistent storage for our K3s cluster. These will also be thick provisioned if applicable, but again, these will just be like our 2 Worker VMs, so for the demo, they'll be thin provisioned. These will be VM IDs 211, 212, and 213, also known as Longhorn 01, 02, and 03. Now, the benefit of thin provisioning is that the VM disk will only take up its used space. In this case, the default I set for Longhorn is 128 gig. That means we'll use 128 gig for each of our Longhorn VMs. Note, in this case, we just use a number here since it's defined as a variable. This can also be increased later, just not decreased. I'll go ahead and leave it as the default for 128 gig. Next, we need to define our VM IP scheme. In my case, my network is 192.168.100, and my gateway is .253. Note that my gateway or my router is the only variable that's not defined inside our format. Then for our VMs, we need an available range of IPs that isn't in use, ideally something that's not in the DHCP range. In my case, I used 192.168.100.90 and ended up at .98. Now, we'll also use .99 in script 3 as an additional IP, but more on that later. But on that note, in script 3, we'll also need another 4 or 5 available IPs in your network. These can be anywhere else in your subnet, but they just need to be sequential. In my case, I used .201 to 205, but again, more on that later. Now we'll go ahead and go back to our Proxmox shell, and there's actually nothing else we have to define here, just these parameters here. But you have to make sure these match your network. Since this is my network, I'll go ahead and leave these default settings. I'll hit save, exit, and run it. So we see that it's starting to clone our VM template and define VMs. It starts with VM 200 and defines the settings we set. And now it's moving on to VM 201. Now, you don't want to click off of our Proxmox shell while this is going, as that may interrupt the deployment process, but what we can do is go back to our GitHub. If I scroll down a little bit more, we can see what's being set. So we saw that our VM 200 got deployed. In this case, this uses 2 gig of RAM and 2 CPU cores. It uses the default 8 gig of disk space. Then VMs 201 to 203, which are our test K3s 01, 02, and 03, these are our control plane VMs. And they only need about 4 gig of RAM each with 2 cores each, and they use the default 8 gig of disk space. Then we scroll down a little bit farther. These are our Worker VMs. They need a little bit more, so they need 8 gig of RAM each and 4 CPU cores. Additionally, they need a little bit more disk space, so on top of that default 8 gig of disk space, they also get an additional 16 gig each. Then if we scroll down a little bit farther, we can see finally our Longhorn VMs. These are also considered Worker VMs, but they don't need as much juice, so they'll be 4 gig of RAM and 2 CPU cores each. But since these are our Storage VMs, they will need additional space, and that's why we've set 128 gig on each of these. Back to our Proxmox shell, and it looks like we can see all of them did get created. And the interesting thing is we can see that it does say what you defined here is about 474 gig, which actually exceeds the total size of our disk. But in this case, that's where thin provisioning shines. If we click here, we can see, and you might not see this because my face may be in the way, so I can go ahead and zoom this out a little bit. The way Proxmox formats things is it actually only gave us 200 gig of usable space for our thin LVM because there's another section of Proxmox that is known as our VZ, which is where our ISO images and our backups are stored. And then there's some remaining that's dedicated to the OS itself. And of that 200 gig of usable space, we crammed all of those VMs within that usable space. Now, before we turn on these VMs, we can see that we only use, surprisingly, about 16 of that 200 gig. But once we turn on the VMs and expand it, it's probably going to use about 100 gig. Okay, back in our Proxmox shell, I'll go ahead and hit up arrow to resume. And then we could pick up on script 2C. But before we start our VMs, it's a good idea to actually confirm what we built. So we want to double check these and make sure all of these settings look correct. We can see that our admin VM has 2 gig of RAM and 2 CPU cores, which is what I defined, with 8 gig of disk space. And if we look at our cloud init, we can see that it does use the IP that we defined, and we can check on the next one. Now, for time's sake, I'm not going to check on all of these, but you would definitely want to. And if these settings weren't right, this would be the opportunity to make them what you want. We can also see our Longhorn VM did get 128 gig of disk space defined. I know this looks a little weird, but that is actually 128 gig. Okay, so back to our Proxmox shell. I'll go ahead and hit up arrow again, then type in ls. Let's go ahead and type in nano and review it real quick. Now script 2C is pretty simple. All it does is turn on the VMs in sequence. This other part here is grayed out, but these are additional code blocks for reference. This section here would turn on the auto start feature for each of these VMs to be started in sequence. If we were to reboot our Proxmox host, each one of these VMs would turn on automatically. This section here is to gracefully shut down each one of our VMs if we needed to. This section here is to hard stop all VMs if for some reason we needed to quickly stop everything. And then this section here allows us to delete all of these script created VMs, but keeps the template there. That way, if we needed to redeploy our VMs, we could have a clean slate. I'll go ahead and run it now. And it says, please manually review the created VMs, which we just did. And we can see that it's starting to turn on the VMs. It shows generating cloud init ISO. Now the play button may be a little bit behind, but it will catch up soon. Now it looked like the play icon was a little bit delayed on these, but it caught up. Okay, now all the VMs are started. Now we can continue on to script 2D. Script 2D is a transitional script. This will be the last script that we run as the user Ubuntu prox. All scripts after this point will be run as the admin VM, which is the first VM in our list. Now we'll review what script 2D does. First, the script extracts the IPs of all our VMs that we defined in script 2B and stores them as a variable. Then it will prompt us if we want to update them. If we pick yes, it will loop through all 9 VMs and update them, which may take a few minutes. Then it waits for the admin VM to be online, and then we'll SSH to it. It will then copy our SSH key to the home folder of the Ubuntu user for this VM. This is because in script 3, the admin VM will then log into each of the other 8 VMs, so it needs that SSH key itself. Then we'll export out a list of IPs for all of our VMs to a text file, which will be stored locally as the Ubuntu prox user, as well as remotely under the Ubuntu admin VM user. This VM IP text file will be used by script 3 to know what IPs to SSH to. Then finally, scripts 3 through 6 will be downloaded and prepped, as all scripts after this point will be ran from the admin VM. Let's go ahead and run it. I'll go ahead and pick yes. Now, since it has to loop through all of the VMs to get their updates, this may take a few minutes for this part. Okay, it looks like it finished updating the VMs, and then it SSH'd into the admin VM, got the SSH key over, and then exported out the VM IP text file, and then we can see all the files that it downloaded. I can even type in ls to get a more colorful response of what it actually downloaded and showing what is executable. Next, let's review script 3. I first want to give credit to James Turland, aka Jim's Garage. Had it not been for his YouTube series, I would not be here making this video series. His series really inspired me to take what he did and improve upon it and show others how to use Kubernetes at home. So I took his script and added a few minor modifications. First of all, his script had you actually define the IPs of each of the VMs in your cluster. I decided it would make more sense to grab those from the text file that was created in the previous script. You can also notice that his script only has 5 VMs, whereas mine has 8. In his version, he later adds additional VMs, such as Longhorn Storage VMs, after his cluster has already been created. I wanted to simplify the process by having all nodes added to the cluster at once. For that reason, there's only 2 variables we actually have to define, which is our load balancer range and our virtual IP address. Our load balancer range is where we need to have a set of available IPs for the sites that we'll later be deploying in our K3s cluster. In my case, I'll be using 201 to 205. Now, this does not have any correlation with the VM IDs here. This is just arbitrarily what I picked in my network that was available. But yes, in your network, you would need a sequential range of about 5 IPs in your network for your load balancer. And the virtual IP address, otherwise known as the VIP, is where our control plane nodes will be communicating amongst each other. These 3 VMs in our network will be our control plane nodes. Even though they have individual IPs, they can act as one IP, which will be this virtual IP address. So that way we'll have some high availability in place. So because of the simplification of his script, we only have to define these 2 variables. Other than my modification on how things are defined and adding the Longhorn VMs to join the cluster in the beginning, the rest of the script is his script. Now, it's probably simpler to explain what it does as it's actually running, so I'll go ahead and run it. The first thing it does is it uses a thing called K3s up, also pronounced ketchup. As that goes through, it will loop through each of our VMs and check for the SSH key. Then it starts getting components of K3s added. Now, fair warning, this will take a few minutes for it to fully deploy. So the first thing it's doing is looping through each VM and making sure that each of the VMs in our cluster have the components for K3s or Kubernetes downloaded. Now that it looped through everything, it starts on the first control plane VM in our cluster, which is K3s 01. This is defined as our master 1 control plane. Next, we can see that the first VM in our cluster, which begins at 91, K3s 01, is now sending information to the next VM in our cluster, 92 K3s 02. We can see that it then moved on to the next VM in our cluster. Now again, since this is going, we don't want to click off of our shell as this will interrupt the deployment process. Just be patient to let this roll out. VMs in Kubernetes are referred to as nodes. A node in Kubernetes is typically either a controller or a worker. Now, in his video series, he calls them master or worker, but same difference. Now we can see that Kubernetes did deploy. It looks like we actually have a hello world deployment already here in our network, which is the first IP in our load balancer. I'll go ahead and browse to that. Since this is port 80, this will actually be HTTP and not HTTPS. So we'll go http://192.168.100.201 or whatever the first IP of your load balancer would be in your network. And look at that. We have a successful deployment of a hello world type page in our Kubernetes cluster. A couple more things I can show you with our Kubernetes cluster. We can type in kubectl or kubecontrol get nodes, which will show the nodes in our K3s cluster. K3s 01, 02, and 03 are our control plane nodes. Then 04 and 05 are our worker nodes. And then test Longhorn 01, 02, and 03 are also technically worker nodes, but these will be later used for our storage. Then we can say kubectl get pods, and the only pod we'll see is our Nginx or Hello World pod, because this is the pod that's in our default namespace. But if I then run the same command, kubectl get pods -- all namespaces, and I want to see all information about them, so I'm going to type in the argument o wide. Well, that kicks back the same information that was up here. So we can see all of the information for all of the pods and their IPs in our K3s cluster. Now we can also see that some of them have the IPs of our network and some of them have a separate network. And that is how Kubernetes works with networking. Typically, you won't be able to access the things that are in this network. You have to expose them to your network by means of a load balancer or by what is also called an ingress. But more on that in the next scripts.